So next up we have Eric, our final speaker from UNSW Sydney, and he'll be presenting a SOC paper on can trajectory generation combine privacy and utility?
Yeah, hello. I'm from the UNSW Sydney and also working with CSIO, and I would like to give you an introduction into trajectory privacy. To start with a story about privacy, you probably know why privacy is important, but still to give you an idea of a case from Reddit, here is a person, and this person moved to New York City because they always dreamt of driving one of these yellow cabs because they saw them all the time in Hollywood. And this obviously creates traces because, for example, we have every trip of the taxi driver. And then researchers come along and ask, hey, can we have these traces from a company, for example, and they get released. For example, there are taxi data sets from Beijing, there are some from New York City, and then you get something like this. So here we see the trace from our person on a random day, and you have the latitude, longitude information, which is obviously a lot more exact in real life, and you have usually timestamps, which might also be more exact. And now what someone actually did from Reddit is they looked at one of these taxi data sets from New York City, and they also looked at the prayer times of the Muslim religion. And what you can see now is that this particular driver, he always had his break during these prayer times, which allowed to infer that this person probably is a Muslim. And if you now think about having a lot of traces over multiple days, you can actually be pretty sure that this is the case. Now, you might say, well, the traces were anonymized when they were released. But as you probably all know, pseudo-anonymization is not necessarily enough. You just need one picture from a Met Gala with Sydney Sweeney, then you can maybe see the taxi driver on this image, and you have a timestamp, a location, so you know exactly which trace belongs to which taxi driver, and then we know of a particular person in real life, we know which religion they follow, which might something they don't want to have in public. So let's throw all the data away. That's a great idea. Data sparsity is amazing, but and if we have no data, there are no breaches. But there are many use cases. You've heard about a few of them before in the session, so that's really not feasible. So, of course, a lot of people have been thinking about this since 2011. I think the first paper was published, and the idea is we take the real data and we do some magic with it, differential privacy, k-anonymity, whatever we are talking about at this conference, and then we get protected data off, and it's all fine. And we wanted to know whether this is actually the case. So first of all, what we did in the paper is we proposed a framework with 5 goals. And we have a lot of detail on each of them in the paper, but just to give you an idea. First of all, we have formal guarantees, which is usually differential privacy today. And this is important because even if we have empirical privacy, and I'm a big fan of it, it might always be that there's a better attack or a new attack, and we have only measured against something. So if we have formal guarantees, we know that we are protected against all future attacks as well. The second thing is the unit of privacy. And this is kind of a subset of the first goal, but you will find that this is something that papers are getting wrong all the time in this space. Because a lot of approaches don't work really well on the privacy side because they are protecting the wrong things. If you look at location traces, a lot of people try to protect the location. They add noise to each location. But if you think of a straight line and you add Laplace or Gaussian noise, you will just get something like this, and then if you just average it, you're back to the real line. Of course, real examples are not that easy, but still, your differential privacy guarantee won't hold if you just use all your budget for one location. And unfortunately, there are way too many approaches doing exactly that. Then there's empirical privacy, which a lot of paper don't, if they have formal guarantees like differential privacy, they don't actually do any experiments anymore. Yet, you will see in a second that there are a lot of approaches where these proofs are broken. So if you had done empirical analysis, you might have picked it up earlier and you wouldn't have released a broken scheme. So I think it's important to do both, the theoretical proof, but also some empirical evaluation. Then utility is quite straightforward, so I won't talk about this in too much detail. The main takeaway here is that everyone kind of uses a new metric, so it's really hard to compare approaches. So if you work in this space, maybe we should try to now consistently use the same metrics in our papers. And lastly, of course, the approach has to be practical. Now, for traditional trajectory protection, there was a really good SOK presented here last year at PETS. So I'm not going into too much detail, but to summarize, we had an attack against differential private protection schemes based on like a deep learning model that uses like information such as street networks and things like that. Then the SOK that was presented here last year from a research group from the KIT, they found that out of the 17 papers they looked at, 10 of them had errors in their proof, so the privacy guarantees are not necessarily as claimed. And then there's another research group from Germany that has looked into utility a lot, and they found that these traditional schemes have utility that isn't really suitable for real-world applications most of the time. So here's the table from the paper, but yeah, I won't talk much more about it because it's now a core contribution, but basically you can see that there's nothing that really satisfies all our goals. So in around 2020, a professor proposed a vision paper on a conference saying, well, if trajectory protection with like these classical schemes doesn't work really well, what if we take real data and then we use some sort of a generative AI, not necessarily AI, it could be a generative scheme in general, and we get synthetic data out, which is fake, so we shouldn't have any privacy problems if we use this, right? Well, we looked at this, and none of the currently existing schemes provides privacy guarantees. They are all just based on the fact that the data is fake. But how do we know it is? What if the model just remembers a sample as it is and outputs the same thing? You can see there are a few approaches that do try privacy, but a lot of them also use location privacy again. For example, this approach here is quite nice. I really like it, but the problem is they only perturb the locations. So they use the entire budget for each location. So if you have a trace of 100 locations and you use epsilon 1, for example, you actually only have epsilon to 100 for the whole trace, which isn't really great. And a lot of approaches are based on LSTM trigon, which I think is like the most cited paper right now. And I really like it, so don't understand that this is a really bad paper from what I'm saying now. It's really, really good at utility. But this is how the architecture looks like. And after working for a long time with it, we found a few things. First of all, you can kind of remove the white part. So this should be a generative adversarial network where we have a discriminator trying to distinguish between real and fake data, playing a zero-sum game with the generator trying to generate fake data, and then eventually the fake data gets really good. But actually what's happening here is that they use real samples as an input, and then the generator modifies these. So it's more like an autoencoder where we have a latent bottleneck, and then we have a noisy output, which means if we train the generator long enough, eventually the fake samples will just become very, very close, if not identical to the input, which questions if we have any privacy. So we thought, okay, we just change this and use noise as the input for the generator, which is how many generative adversarial networks usually work, especially in the image domain. And we thought, okay, this is like just another domain, but this has been a lot of times for image generation, audio generation, medical data generation, where they used it for ECG signals, which is also sequential. So we thought, okay, we use just one of these models, and then first of all, we have a noise input, and then in the next step, there was a differential private GAN models, so we could just add differential privacy to it, and then we actually have a generative model with DP. Well, it turned out it's not that easy. So here you can see, I think we looked at 6 models that we actually implemented and released the code for. And first of all, we tested it on IMNIST. That's an image data set, but we followed the approach from a medical paper where they proposed to actually look at the pixels as a sequence. So we do not generate this as an image, but we actually generate one pixel like at a time. And the idea here is just that we have a very easy first test, like a toy data set, because we use the sequence of 28 times 28, so 28 timestamps with 28 pixels each, to see whether it generally worked. And while that worked, once we went into the image data sets, into the trajectory data sets, sorry, it completely fell apart. You can see no approach produced anything that looks remotely useful. Yeah, we've been working on this for a long time, and if you just think, well, maybe I'm just really bad at deep learning, we released all our code and we tried to make it really reusable. Like we wrote a framework with like base classes, and it should be really easy to like reproduce it, hopefully. So feel free to go and try to fix this if you can. Yeah, but we came to the conclusion that really you can't just take any GAN from like another domain, like the ECG signals, and apply it to location trajectories, because the two-day nature and the high complexity of this data just makes it really hard. So right now, while these generative approaches have a lot better utility than our traditional DP approaches, they do not have formal guarantees just yet. Nevertheless, I do still believe that this is a really important research direction. I just think that we actually need to put in a bit more work and design a custom generative model for this domain. And once we have a model that would work without input during the generation phase, we could then apply differential private stochastic gradient descent, or maybe relaxation, like label differential privacy. There's a really good paper on this in the location domain that we also mentioned in the paper. And maybe this way we could actually get a generative model with guarantees. And that's what we are working on at the moment. Thank you.
Any questions from the audience?
Thank you for the interesting work. I was wondering, sometimes in practice it might be okay that we don't have the formal privacy guarantees. Does any of these papers that does not satisfy the formal guarantees, do they recognize it and maybe say, okay, even though we do not achieve pure DP or some relaxation of DP, maybe empirically this is, let's say, sufficient?
So yes, let me go back to the slide. So here, for example, LSTM trigon itself, it actually tested the trajectory user linking attack, where the idea is...
Hasn't turned up yet.
Oh. Yeah. So this paper, they looked at trajectory user linking attack, where the idea is that you have a lot of trajectories and you have user IDs, and you kind of want to link them together. So you want to see whether trajectory belongs to a certain user. And they use this as an evaluation because they said that's a really common attack. And against that one, LSTM trigon actually protects it. However, the problem is that it is based on a lot of engineering choices. So if you train the model for longer, for example, because it's basically an autoencoder, this doesn't necessarily hold true anymore, because the outputs get more real the longer you train. The same if you just use smaller trajectories, for example, and you still use the same latent dimension. This also doesn't necessarily hold true anymore. So if you use it and you really know what you're doing, you could, for example, use LSTM trigon to protect against this particular attack. But we also applied another attack, the erupt attack, and against that one, for example, you wouldn't have protection. But if you kind of have a very particular attack in mind and you are sure that you really only want to protect against this, there are approaches that consider that, yes.
I have one. Slightly different trajectory generation. You mentioned very early on that we love coming up with new privacy metrics, and we never seem to use the same privacy metrics across our pieces of work. And you mentioned there, maybe we need to come to some kind of convergence.
I was, in that case, more talking about the utility metrics.
Oh, okay.
In terms of privacy metrics in this space, it's actually fairly good. Like everyone is kind of agreeing that differential privacy is the gold standard, and there's very little deviation from that.
All right.
Yeah.
So for the utility metrics,
yeah,
what do we do?
So they're pretty much it is being repeated in every SOK. Like I think the SOK from last year, they said the same thing. So what I try to do here is that there are now 2-3 metrics that have been used by more than one author. Usually every research group has their own set of metrics. So what we try to do is we defined 2 axes kind of, and so that you take metrics out of each category. So we have 4, along the axis you have 4 fields. And then you kind of at least know that you've covered everything. But yeah, in the best case, paper would look at the related work and they would just reuse the most common metrics that have been recently used.
Great. If we can thank the speaker again and thank all the other speakers as well.